All the patter.
Yeah. Okay. And live on custom stream. Got it. You're on.
Good evening, everyone, and welcome to the March Coast Guard Tech Talk on basic chart plotting. I'm your host, PJ O'Neill, Branch Chief for STEM Training in Youth Programs. We're very lucky to have with us tonight Doug Ledgett, Shepard, Zedaker, and Dane Hahn to present the material for us tonight. So I do want to welcome everyone that is on our Zoom call as well as Facebook Live. And just to note that the Tech Talk is being recorded and will be posted to the Aux Scout YouTube channel. And I encourage you to share this information with your shipmates that you can use the Tech Talk as a training material in your Sea Scout ship. One last note before we get started. We will take any questions that you have in the chat box, and as well as questions from the Facebook live stream, and we'll moderate the questions towards the end of the presentation. So feel free, if something strikes you during the presentation, to pose a question, and we will get to the question at the end of the presentation. So with that, I would like to turn it over to our team, Shepard, Doug, and Dane.
So we're going to be going in that exact opposite order as we make our presentation, and which is fine. So I'll be starting off. Doug's going to pick it up, and then Shep's going to wrap it up. And so that's our plan. We took a look at the content of the material that could be applied to the title that you've given this, and decided that you didn't want, a 72-hour program. So this is pretty much as boiled down as we could make it, but we're willing to expand in many areas if somebody has a question. So
Outstanding.
yeah. Now, we haven't really done a dress rehearsal. We thought we would, but time got in the way. So this is it. This is raw and unedited. So you'll soon see what I'm talking about. I really wanted to have this just come on like it was a TV show, but it's going to take a minute. There we go. You're getting there. I'm hoping that you can see this slide. Is that something that
Yes,
you
you're
can?
good.
Okay, that's good. So this is our plan. We're going to be talking about the globe that we live on. We're going to be talking about how it is that we identify where we are on that globe, and then how we keep track of that by using charts, and then in the third section, learning a little bit about how to figure out where you are on a chart, and how long it will take you to get from where you are, if you know where that is, to where you want to be, if you know where that is. And so that's kind of it in a nutshell. And I'll just roll through at this point. Finding your location and your destination is really the 2 points that we want to establish, and then all the pitfalls that are between your location and your destination. So this is really elementary. The course covers navigation skills that we believe are important for people to understand a chart. And we're not going to get into chart number 1, which is a wonderful thing to have and is downloadable. So if anybody wants to learn more about charts, you can download chart number 1. And it's about, well, I can't tell you how long it is when you download it, but my copy of it in a book runs around 75 pages or so. So it's interesting reading, let me put it that way. And the whole idea is that you'll understand the chart and be able to plot a course. Maybe not as soon as we're done, but at least you'll understand what the rudimentary items are that will get you there. So the topics here, we're going to be looking at marine navigation briefly. We're going to be I'll be spending quite a little time on latitude and longitude, and also different projections. And we'll talk about what a projection is in a few minutes. And then basic charts and chart symbols and geometry. If everybody has gotten an A in geometry somewhere in their life, they won't have any trouble at all with it, with charts, until they find how shallow the water can be here and there. And practical navigation tips just to keep in mind. So here's what the Earth looked like long before you were born. For thousands of years, humans were pretty sure the Earth was flat because it was flat where they lived, and that the ocean water simply spilled over the edges. And that was basically the Earth that they lived on. Columbus didn't believe that, although even as late as the late 1400s, this was still a pretty common way of thinking. And some of Columbus's sailors were totally afraid that if they sailed too far, they'd go over the edge. And I guess that was, that's if you're afraid of something, you'll figure out a way to make it happen, or make you afraid. That's just the way it is. And I would reference the coronavirus as my point right there. But anyway, good news. Columbus was right. The Earth is a globe, and it looks for all the world like what we're seeing in this picture. It doesn't have any lines on it. It doesn't have any cities on it. It's just a globe. It's a big blue orb in space. But how do you find out where you are? You know what? Knowing where you are is easy. I'm right here. I know where I am. The real question is, where am I in relation to you? Or where am I in relation to that mountain over there, or the ocean over here, or whatever? So when you begin to try and figure out where you are on a map, it's a little bit different. And you want to know where you are on a map, and you want to know where you are in relation to other people and other things. This was very difficult to determine. The early maps are full of errors because they just didn't have a good grasp of cartography. But it got better and better and better. And we thank people like George Washington for doing so much of the land surveying that he did. And we thank the scientists in England's Greenwich Observatory. It's a wonderful observatory, and it's only about 25 miles sort of southeast of London. And it's been there forever. And the scientists who were there devised a way to give every part of the Earth an address. Every part of the globe has its own address. These are the lines of latitude and longitude. And they determined, because they could, prime meridian should go right through the Greenwich Observatory. And it does, oddly. So that they have a big orange stripe that is the prime meridian that goes right through their parking lot and through the building and out the other side. It's fascinating. So they established these lines of latitude and longitude, and they picked the prime meridian and the equator as the two items that would make the cross on the Earth. And then everything goes from there in both directions, up and down and sideways. A little hard to say up and down and sideways about a globe. But anyway, that's what we're going to see in our depictions of it. So that's how they standardized and how we determine where we are. By the way, do you know where you are? Do you know your latitude and longitude? I'm going to suggest that if you have a smartphone, I don't know who doesn't anymore, but you may have to borrow one if you don't. There's tons of information in a smartphone. And this is my phone, and I wanted a picture, so I just did a screenshot of it. Just take your smartphone and go to the compass. Obviously, this is the compass, and down below the degrees, the heading degrees that tell you what the arrow is on, is the latitude and longitude of where I was sitting when I took this picture. I'm in Englewood, Florida. I'm at 10 feet above sea level, and this is the latitude, and this is the longitude. So, and you want to check on those. Let me just say that if you don't have a smartphone, I bet you do have one, but if you don't have one, or if you have one that you can't seem to find the compass in, you can always download Seatow or Boat US. These are their apps. Both these companies are really insurance companies that have towboats. And if you run into trouble while you're out on the water, you can just click on their app and call them. Push the yellow button here, and your phone will call them, and they will say, "Where are you?" And you will say, "Oh, look, right here on the middle of my Seatow application, the latitude is 26 degrees, 59.36. I say 59 minutes and 36 seconds. Or is that a percent?
It's a point.
Looks like a point. So,
Yeah.
okay, so it's 59.36 seconds. Minutes, I should say. And here's the longitude. So, and these pretty much match because I did them at the same time without moving. So here's the latitude and longitude on Boat US. So if you have one or the other of these apps, Boat US has a weather feature that is at the bottom here. But I think Seatow is a nicer design. This is the one that I recommend. They're both free, so I don't make any money on recommending them, just FYI. They both have latitude and longitude, and for you, wherever your phone is, they'll tell you where your phone is. So that's the story on those. But what is latitude? Well, latitude is the distance from the equator along the horizontal axis. This is the equator, and it is the horizontal axis. Okay, it's 0 degrees, and the numbers go up as you go up, and they go up as you go down. That just to keep you on your toes. So the North Pole is 90 degrees north, and the South Pole is 90 degrees south. The equator is at 0. So this little point where they cross would be 0, 0, 0, 0. It would be latitude of 0 and longitude of 0. So everyone knows where that is. Well, you do now. And so as a question that you might want to mull over, what's the maximum possible latitude on Earth? Well, it's 90 degrees. So you could be at either 90 degrees north or 90 degrees south, but there's no greater latitude on Earth or anywhere else. So that's what latitude is. So we know now that latitude is the measurements north and south. And longitude is the measurements east and west. Again, from the prime meridian to go east, you can go east 180 degrees, and you can go west 180 degrees. And oddly, when you get out to 180 degrees east or 180 degrees west, you're in the same place, because that's the one spot where the numbers are exactly the same. But what do you suppose is on the back side of the Earth? If the prime meridian's on the front, there must be something on the back. Not hearing anyone jumping up and down, I would say it's the international date line. It's where we change days as we travel. So, but that's not part of today's presentation, although it will reappear. So that, again, the prime meridian is at 0. Longitude is the distance from the prime meridian along the x-axis to wherever you want to go. So for example, if you were going to measure, let's say, Japan, you would be going you'd be going east, till you got to a point where your navigation tools told you that Japan was directly north of you. And then, so you would know how far east you had to go. And now you will know how far north you'll have to go. That, I don't want to make that any more confusing than it already is. But I will say that if the Earth becomes one large sphere like this, and then this is exposing all one side. So this goes out to 90 degrees on both sides, and we draw it into quarters. Then what we have is everything in this quarter is north, because north is north of the equator, and west because this is the prime meridian, and so we are west. So everything in this area is going to be certain degrees north and certain number of degrees west. Okay, that's just something that you'll be happy to know. Again, prime meridian and equator. That's what we're looking at here. So, and again, this is what I was just talking about. If we divide the Earth into quadrants, our quadrant is the northwest quadrant. All our latitudes are going to be north, and all our longitudes are west within this quadrant. And so every point in the United States is going to be north and west. Now I've said that 3 times, so that's good for you to know. This is what's on the backside. This is the international date line. Now, ideally, it would be this 90-degree line that would go from pole to pole, from the North Pole to the South Pole. But politics has gotten in the way a little bit. So the line has gotten a little crooked. And most people didn't feel that it made a lot of difference. For example, the Aleutian Islands, which are part of Alaska, it made sense for all the people who lived on the Aleutian Islands to be in the same day as each other, because this is the day line. So this side is Saturday, this side is Sunday at a particular time of the week. But it's always, this side is always one day ahead of this side. So the Aleutian Islands, all the islands are in the same day. And as you get further down here, these were some other sets of islands which decided that they wanted to be in the next day over. So they've got this sort of a big gerrymander here that makes them part of Sunday in this particular picture. And there are parts of the United States that are over in this area. American Samoa's over here, Guam's in this area. So Midway Islands over here. So those are in a different day than the rest of the United States. But this is the other side of the prime meridian. Then this falls along the 180-degree longitude line. But again, it's been modified to allow the convenience of various groups of islands. Now, let's assume that you had, as a child, you had a globe that was something that your grandparents gave you so that you could spin it and you could look at the various countries as they spun by on this globe. If you had peeled the paper or plastic or whatever they use to print this off your globe carefully, it would look about like this. This is the first effort that cartographers, map makers had made to try and depict a globe on a flat surface. And that's what we're doing with charts. Charts are flat, and the world isn't. So this is how we try and depict the world when we're looking at something that used to be a globe. Now, this isn't the only way we do it. There are lots of ways we do it. This is a Mercator projection based on the Belgian geographer and cartographer, Gerardus Mercator. And his concept was that we would take the globe, or a globe, and this globe, if you can visualize this as being made of glass, let's say, and all of the parts of the Earth were painted on in like a transparent paint. So oceans would be blue, and and land might be brown and so forth. And the lines on the globe would be visible. Then you put a light in the middle of the globe and see what it casts out on this cylinder that's wrapped around it. And ideally, if you do it correctly, you're going to get a drawing like this drawing here. So this concept is, how do we take a globe and make it a flat map? This is one way of doing it. So Mercator imagined the light in the center of the globe that projected the Earth's features onto a cylinder wrapped around the equator. All the lines remain straight and true when you do it this way. And that's important because other projections don't have straight lines. They have curved lines. We'll get into a couple of other projections in just a second. But this is an ideal way of showing what is out there. Now, what happens here is that as you get further up, there's distortion. So it's accurate at the equator, this being the equator line right here, the 0 degree line. And this first box is essentially square, but the next one up becomes a rectangle and the one above it gets even bigger and so on. And that's just because that's the way a projection works. The line stays straight and true in both directions, but it gets distortion as you get closer to the poles. For example, Greenland isn't bigger than the United States, but it looks like it is on this map. Okay, just so you know, those are some of the things that get discussed. Here it is again. The Mercator projection became the standard projection because routes following an unchanging compass bearing are straight. So you could use this projection to plot your course. And if you, whatever line you drew, if it was straight on this map or this chart, it was going to be a straight line that you were going to be sailing, as opposed to a polyconic projection. This projection really is accurate at the poles and gets grossly out of accuracy as you get closer to the equator. And it's just a little different way of doing it. These grid lines are all curved. And so plotting a course, while easy if you're only going a mile or two, is very difficult if you're hoping to sail to Portugal or, let's say, Hawaii, depending on which coast you're on. So stepping back from that portion, let me just say that about every 15 degrees around the Earth, the time changes by an hour. And we use Greenwich Mean Time as our base mark. So when you are quoting time, let's say in the Chicago area, it's Greenwich time -6 hours. Okay, so if it's 6 in the morning in Greenwich, it's midnight in Chicago. And that's because the Earth's rotation goes in this manner. And that means that the sun comes, the sun doesn't move, but the light comes in the opposite direction. So it's always later as you go further and further west. And talk about time zones a little bit. There are 24 time zones in the world, our world. Actually, there's a few more than that. Some are a little bit more political than others. But we have 5 zones in the United States, and that runs from Alaska to Maine, basically. Then we have some possessions. Guam is part of the United States, and American Samoa and stuff like that. So there are additional time zones besides that. Russia, on the other hand, runs from about right here all the way past Siberia. So they have 11 time zones. Now, that's a lot of time zones. We have, again, 4 across mainland US and then 1 each for Alaska and Hawaii. So Eastern is Greenwich Mean Time -5. That's how it's shown. The middle the middle area here, central, is Greenwich mean time -6, and mountain time is Greenwich mean time -7, Pacific is -8, Alaska is -9, and Hawaii is -10 hours. So those are the US time zones. And now let me introduce Doug Ledgett, who will be picking up right here and going on into basic navigation.
Okay,
Thank you, Doug.
thank you. We'll share up here and see if we can make this whip.
There it goes. Yeah, it's going
Looks
good.
good.
All right. So what's basic navigation? Well, as Dane's explained, it's learning to find out where you are relative to your surroundings. And we talk about the tools of the trade, which Zip will be talking about shortly. How do we understand a chart? What do we know about local knowledge? Because that has a lot of bearing on what we know and don't know and how that chart would affect us. And we need to learn a little bit about speed times time equals distance, which way to go to get where we want to be. So what makes a map a chart? You know, our maps on the roads are flat, but when we talk about charts, we talk about things that have under the water depths, contours, soundings, things like that. So when we add those to a map, it becomes a chart. And these figures that we see on charts are very important if we're navigating through areas. And we'll talk about that in just a moment. Charts are graphic representation of our surroundings. So they're similar to a map. They let us plan and plot our current location and our intended location. And then we can determine how long it will take to get there if we're going at a certain speed and what directions do we have to go to get there. Because and we'll talk about it a little bit, but we can't go in a straight line all the times. We need to kind of figure out how to get around obstacles. So what do we look for on a chart? Well, number one, we have a chart number. Every chart around has a number. And you can look that number up and it will tell you basically what that chart is. This just is a representation, and it's an old one because it still has Loran on it. But it's east coast of Massachusetts. It's the Nantucket Sound and its approaches. So that tells us the location and the title. It talks about the chart projection, and it's a Mercator projection. And we'll get back to this in a little bit, but it says a scale is 1 to 80,000 at latitude 41 degrees, 25 minutes. That's important to know, particularly the scale, because it changes what our distances on that particular chart are when we're trying to measure them. The other thing that we need to know, and it's very important, is the vertical datum, and that is soundings in feet at mean low water. So you need to look at the tidal block on a chart to determine particularly what these figures, and these happen to be Loran figures, not depths, but I'll show you another chart in a little bit. But is it in feet or is it in fathoms? A fathom is 6 feet. So if you were looking at a chart and you thought it was in fathoms and it showed 3, you might think, well, I have 18 feet of water under me. But if you look at the vertical datum printed on the chart, and it says it's in feet, you only had 3 feet. And if you drew 4 feet, guess what? You were aground. So we measure distance. And all the charts have some type of a scale, and it tells you what the distance is. This happens to be on a map, a chart, that it has a scale of 1 to 40,000. And as you measure that, it tells you what 1 nautical mile is, and it tells you what 1 statute mile is, and you can figure it out in yards. And all these little ones down here are in tenths, basically, of what would be this 1 nautical mile. So you look at your scale and you can use a set of dividers and you can figure what your distance is based on say it's 1.5. So you could put 1 point on here and go over here to a half, and you would tell that on a scale of 1 to 40,000, if you had that much distance between your points, that would be 1.5 nautical miles. So what is a nautical mile? Well, we'll get to that in a minute, but 1 minute of latitude is always 1 nautical mile. So 1 minute of latitude. That's about 6,076 feet. Most of us just use 6,000 feet, or about 1.15 yada yada miles. So if you look at this projection down here, and you notice that the latitudes are going across here at 10 degrees, 10, 20, 30, 40. 1 degree of latitude is 60 minutes of arc. So if we have 60 minutes of arc and 1 minute is 1 nautical mile, if we go 1 degree, we've gone 60 nautical miles on the chart. So if we move from 0 to 10 degrees, we've gone 600 more nautical miles. Just simple math. This just tells you kind of how it is figured, and it's another appearance of your equator line, and you're increasing over here to 90, 180 to the back, or 0 to 90 to the North Pole and to the South Pole. So that's how we measure distance when we're trying to work with our charts. Longitude scale should not be used to measure distance. And we have scales on our charts back up here that are both latitude and longitude, but if you're measuring distance, you should always use the latitude scales, not the longitude scales, because they're not as accurate. So we got some ways to determine where we are. Don't forget your compass. Well, what's the problem with compass? Well, compasses are based on the magnetic north. And if you put them near metal, or you have some kind of electrical interference, it may turn your compass. I can tell you this from experience. When we were kids, we left Chatham on Cape Cod and we went to Nantucket, and we didn't have a compass to get home. So we bought a little one and laid it up on top of the console in front of our helm. Unfortunately, it had a metal piece under it, and we went due north and wound up over in Martha's Vineyard, which was due west, because it turned the compass that far off, 90 degrees. So know what your compass readings are and watch what they're near. So why do we have a compass? Well, a compass will tell us where magnetic north is, but magnetic north is not the geographic North Pole. And magnetic north changes depending on where we are on the Earth and depending on what our time is. So we have to have a way to figure out where we are if we're looking at a compass in relation to our geographic North Pole. And we do that on our charts with the compass rose. So as you look at a compass rose, and these will appear on your charts, true north is always shown with a star, and it's the outer ring is the true compass readings. And excuse me, back up. There we go. So the outer ring is true north in the true north degrees, and the inner ring is the magnetic north in the degrees based on magnetic north. Well, if the magnetic north moves in time in relation to where you are, you need to look to the inside of these compass roses, and it's going to tell you there's a variation in what the annual increase is between magnetic north and true north, because a lot of times we want to know what true north is, and our compass is telling where to go, so we need to figure out what our actual course is going to be. So in this case, the variation is 1559 west, and that was in 2010. And the annual increase is 1 minute. So if it is now 2022, we have to add what? We have to add 12 to this to get to 2022, right? So we have to increase it by 12 times. So we're increasing our variation by 12 over this number here. And that will help us determine what our present magnetic north is based on that chart at that date and where that chart was located on Earth. Sounds a little bit of confusion, but when you get to use it, and Shep is going to talk about what tools do we use to figure this out a little later in the program. So if you look at a large scale chart, you'll see a lot of different compass roses. And these, because you are in different areas, they will have different variations in the center of their compass roses, because it depends on where you are on the Earth at the time and how much that change has occurred. So when we're looking at charts, your normal typical nautical charts range from a ratio of 1 to 2,500 to 1 to 10 million. We were having a little discussion earlier, a chart of 1 to 10 million probably shows you the east coast of the United States and the west coast of Europe. Between these two extremes, they can be collected into groups like berthing charts, harbor charts, approach charts, coastals, generals, and big overview. And again, I just want to show this projection. You should always look at the scale and what it was, at what latitude that was taken at, and what the soundings in feet are. Is it in feet or is it in meters or fathoms? So this is an example of a harbor scale. You can tell it's pretty large projection. If you had a harbor scale, it may have a chart that shows just what it is inside this, and this is on Martha's Vineyard, inside this harbor. But you can tell, and you look at these, if you look at those figures here, the chart's probably going to tell you these are in feet. So it's very important to know whether you're, again, looking at feet or whether you're looking at fathoms. This would be a scale of 1 to 40,000 of the same area. So this is the Vineyard Haven entrance. That would be the Vineyard Haven entrance, but with a larger scale. And again, it's hard to see, but these are compass roses over here. We can go out to a scale of 1 to 80,000. And this is the same harbor we wanted to look at. But now we've looked at a very large projection that's taken us way off the coast and going up toward Nova Scotia in that area. And here is one scale of 1 to 200,000. And here is that original little Martha's Vineyard area. This is Cape Cod. This is going up here to the Maritime Provinces. So that's why it's important to know what your scale is and what you are looking at. So getting local and regional information. Charts provide the local and regional data in a paper format. So if you had just a GPS, it shows you latitude and longitude, but you don't really know what to do with that. It tells you where you are on the Earth at any one particular moment at a spot, but you can't do any plotting from there unless you have a chart plotter. And those are things that we'll talk about in another session. So how do we move from one place to another? Well, a straight line is the shortest distance between 2 points. But that may not be the safest way to go. So that's why we need our charts to figure out what is the safest place and how do we get from one place to another. So we want to go from point A to point B. Okay, good straight line. Well, we're going along here and we've got 21 feet of water and all of a sudden we're down to 1 foot of water. Well, we can't go that way, can we? So what we need to do is find a waypoint. So as we are calculating our route to be and where we're going to move, we put a waypoint in here, and it says we can go a straight line from here to this point A, and then we do a little dog leg, and now we can get to our final destination. And we'll go around this sand area here that is very shallow. So we wind up plotting in this little waypoint, and this is the course that we need to sail to be good to this point. When we get to that point, then we are plotting where we're going to go into this harbor. So that's the best way to get 2 legs to avoid shallow water. So if I've had any questions, we'll hold them to the end, because at this point, we're going to move to Shep Zedaker. Shep, it's your turn.
Excellent. Okay, I want to X you out and share me.
There it is.
Let's see if I can get slideshow going. And so can everyone see that? Am I
That's
on
good.
your slide that you ended on, Doug?
Yep.
Yes.
Very good. Okay. So Doug and Dane introduced you to the basics of navigation, but now comes the nitty-gritty. How do you actually solve the problem? Okay. Easy to say, easy to see when the lines are on the chart. How do you put the lines on the chart? Okay. So these are navigation problems that we encounter. I say problems. They're really questions that you would have as a navigator. How can I get from one place to another? Okay. So the first thing that's important to know is, where am I right now? So what can I put a point on a map where I am right now? Or do I know the latitude and longitude that Dane pointed out is the basis of our address, if you will, for the entire globe? And so, and then what course should I steer to get to that new place that I want to go? How do I determine that? And how far is it to that place, and how long will it take me to get there? These are the basic questions of navigation or navigational problems that we have to solve in any exercise or going from point A to point B on the globe. It doesn't matter if you're going from Martha's Vineyard to what's a little island off of Martha's Vineyard, or from Boston to London, same problem. Anyway, so what we've devised here is a kind of a fictitious, a fake chart. It's not real, but it's one that's just made up with all the basics of charts that you might expect to see. This is a small scale, so it's a very localized chart, if you will, showing, these are not real places, but doesn't really matter. They have the features that many charts have. And if you haven't looked at a chart before and you don't know what these symbols and things all mean, I've just gotten some pictures here that would give you an idea of what you might see on the water if you're actually at a place. So you see this mark up here, it's G3. So, and it's got a little magenta dot right there and a green triangle diamond above it. What that actually is on the water is something that looks like this. It's a buoy with a light on top, okay, that's painted green with a number 3 on it. That's actually what it looks like. So that's what you'd see from the water if you were sitting in the water right next to green 3. Here, if you look, that's called Fire Lookout Tower. Okay, and over here, if you will, can everyone see my arrow? Can you actually see where I'm pointing? My marker? Yes?
Yes.
Yep.
That's a picture of, let's say, perhaps that Fire Lookout Tower right there on the end of that island, as you might see it from the water. And then down here is another place, Sherlock Shoal. And so here's a picture of what Sherlock Shoal might look like from the water. It's a rock. That's that big X there sticking out of the water that you definitely don't want to run into. So you better know where it is if you're going boating around this particular area. So so that's our chart, okay? And then we need some tools to solve these problems or answer these questions. How do I get, where am I? How do I get to where I am? Where is it? What to do? So you need a chart. You got my chart here. You need a sharp pencil, very sharp pencil, okay? Because you're gonna be drawing some lines, all right? So you wanna have a sharp pencil, all right? You need a set of parallel rules or rolling rule. And so this is my parallel rule that I use to do all these marks, and I'll show you some pictures about that. And then a set of dividers is handy. Here's my dividers and what they might look like. And I got some close-up pictures of those things. Here's parallel rules. And basically what they let you do is determine a heading on a compass rose from a line you've drawn on a chart, and the arms are connected. And so they keep the edges of the rulers parallel, you see, okay, when you move them. And so you can move across the chart and connect your line to the compass rose that you might see right there. I haven't seen one of these for decades. I'm not sure why they still use, or who still might use this, but it's called a parallel roll plotter, and it never worked for me. It doesn't work for most people, but leave us to say that if you rolled this across and these little wheels turned at the same rate, you could do the same thing with a parallel rule, but mine never worked. And so I sold it and bought the parallel rules. They're much better. But you do need a good set of dividers. Dividers are really neat tools because they let you mark points on a chart. They can draw circles if you replace one of the points with a pencil, okay? And also they let you know the distance between 2 points on a chart if you know the scale, or you can lay them up against the side of a chart with regard to the latitude, because that's the only measure that actually works. Longitude, as you know, okay, is going to, on a Mercator projection, which is most of the charts that we use, is going to squeeze as you go toward the poles. And because it does so, that measure doesn't stay the same. But with regard to distance, the latitude always stays the same because 90 degrees is 90 degrees. And the 1 minute of arc equals 1 nautical mile always stays true. So up in the upper right-hand corner of the old chart we were looking at, you had this green number 3 that we saw a picture of. And if we wanted to determine its latitude and its longitude, okay, we would simply line up our parallel rules. We'd go down to green 3 or over to green 3, and we would find that lined up with our scales at a particular point. And you have to pay attention to whether the scale is going up or down in a particular region. In the northwest, of course, quadrant that Dane explained, it always goes in the same direction, so we don't have to worry too much about it once we've recognized what it's doing. So this is 83 degrees and 15 minutes on our longitude scale, okay? And then so it must be decreasing as we go this way. Well, how is it decreasing? Each one of these pairs of light and dark segments equals 1 minute, if you will, okay? And so we've gone from 83:15, 83:14, 83:13. So we're decreasing as we're going from left to right on this particular chart. And then this is a little bit less. Let's call it 83 degrees, 12.1 minutes. Oh, changing things I don't want to change. Touching the wrong thing. Okay, so does everybody kind of understand that concept? We'll go over it again, so you'll see it again, and it'll help you. On this scale then, of course, up is going to be increasing, right, in latitude. Okay, so this one's pretty easy. Where is green number 3 located? Well, we know this is 54 degrees, 35 minutes north. And remember that I said that each one of these dark and white sections is a half of a minute. And so here's 54:35. This must be 54:35.5 minutes, if you will, of latitude. So that's pretty easy. What if you're just someplace? Okay, so what if you're not looking at a particular mark, but you're saying, I think I'm right here. Or maybe you fired it up on your GPS, okay, and it told you where it was, but where am I on the chart? Okay, same drill, okay, mark that point, take your parallel rules and stretch them out both horizontally and vertically, and we would find that the longitude of this point where we are, let's say we're right here in this circle, okay, is 83:21.7. Well, how did we figure that out? Well, it's 83:25 here, right? 24, 23, 22, and a little bit less, 21.7. Okay, and what about our latitude? Well, we know it's 54:35 here, and looks like it lines up exactly there. Should be 54 degrees, 34.5 minutes north latitude. I haven't expressed that enough, and I should. This is west longitude. This is north latitude, if you will. So that's how you plot a position from latitude and longitude. That if you said, I'm just off a jigsaw island, looks like I'm midway through, where the heck am I with regard to latitude and longitude? And that's how you find it out. You see this sneaky little thing over here? That's that compass rose that both Doug and Dane have been talking about. So let's do a little bit more in that sense of distance and bearings and that sort of thing. And so let's say we're trying to go from, this is again our fictitious chart, this red 6 to this green 7. Okay, so that's what we're trying to do. And what's the distance between those two places? Well, you take your trusty dividers, right? And you put them on the points of red number 6 and green number 7, okay? And then you transfer over to the latitude scale because the latitude scale stays consistent in the Mercator projection. So you don't have to worry about that. You can always use the latitude scale. Doug pointed out that the bottom of the chart has a scale on it, and that is consistent over the area that a chart usually covers, but you can always use the latitude scale as well. And so that's what I generally use as a rule. Okay, so what is that distance? Well, here's 1 minute, right? There's 2 minutes, there's 3 minutes, not quite 4 minutes there, okay? And so what is that going to be in terms of distance? Not quite 4 minutes. Let me go back. So 1 minute, 2 minutes, 3 minutes, 3.45, whatever it is, you'll have a more accurate reading when you're using your own dividers than I was able to do from this fictitious chart. So here's a more complex problem where, okay, distance is nice, location is nice, but what compass course should I steer? How would I know what to do? So once again, we take out our trusty parallel rules, okay, that allow us to transfer one straight line over to another place, okay? And we've drawn a line here from this point off of the face, if you will, which happens to be at 8320.5, okay? And we want to go down here to this red nun number 4 that was on your chart to begin with, okay? So we need to know what direction that we should steer. Remember, Doug talked about just transferring this over to the nearest compass rose. You always choose the nearest one because magnetic variation changes over the face of a chart. Many charts will have many compass roses. So you always want to use the closest one to your particular line that you're going to run. So we transferred this line over here using our parallel rules to this particular compass rose. And we found out that the true bearing down here that we read is about 211. And also the compass bearing, because of variation, the difference between the magnetic north and true north is about 4 degrees. That's a compass heading of 215. So if you had a chart plotter GPS on your boat, you could run 211 true, okay? But if you only had a compass in your hand like Doug did, be sure not to put it next to something magnetic, okay? Maybe you should have one of these, which isn't generally interfered so much. This is called a flux gate compass, okay? So if it's around your neck and away from magnetic things, you don't have to worry about it. You can read exactly the magnetic bearing that you wish to take. So you're going to start here and you go to there and you're going to run a compass course of 215 degrees. And that'll hopefully get you to red number 4, at least close enough. Once you see it, you'll know where to go. Okay, how far is it? Again, take your dividers, okay? Take your dividers, mark from point that you started at to the red number 4, transfer them over to the latitude here, and you'd find out that that's about 3.3 nautical miles. So here's 1 nautical mile, here's 2 nautical miles, 3 nautical miles, and a little bit, about 3.3 nautical miles. So, wow, okay, how can we put this all together? So those were kind of easy. Now we've got no markings whatsoever. We're not going exactly from one buoy to another, okay? We're gonna go from this point 1 that's kind of inside Jigsaw Point, close to red number 4, but not really on it, to over here to this point, which is near Bulge Island and the fire lookout tower, because we want to take a hike and have a look at the fire tower, but we're not going to go exactly to green number 5. And so, oh, that's a mystery. Okay, how do we get from point 1 to point 2, okay, excuse me, to point 3 along this line, which we call 2 here? And when are we going to get there? I mean, it's almost lunchtime. How am I going to get there? I need to get there in a hurry. So what are we going to do? Again, we'll take our parallel rules, okay? We'll draw this on our chart with our sharp pencil, remember, and a straight edge. And then we're going to transfer that line over to the compass, and we're going to find out the nearest, again, compass rose that we can. That's about 106 degrees true, or as we found out, +4 degrees, I think it was. Yes. And so that would be 110 on the compass bearing or magnetic heading. That's what we would run. Okay. What about the distance? Well, again, we would take our dividers, right? And we would put our point on the mark number 1 and our point, the other point on mark number 3. And then we transfer this over to the latitude scale. Okay. And if we did that, we would measure that out to 5.4 nautical miles. Excellent. So we've got a distance, we've got a bearing to run. Still don't know exactly when I'm going to get there and how hungry I am. So there's another little clue here that's written on the chart already, and that is our boat is going to transit that course at 10 nautical miles per hour, which we otherwise call a knot, if you will. So a nautical mile per hour is a knot, if you will. So we're going to travel at 10 nautical miles per hour. Okay, so now we got a math problem. Most people that are young people, even adults, roll their eyes. Oh, math. Oh, I hate math. Okay, can't do math. But it's really not very difficult. Okay, so here's what we know. We're going to start at 14:52. That's 2:52 p.m. for those who are not used to military time. And we know they're going to travel 5.4 nautical miles. And we actually also know that we're going to travel at 10 nautical miles per hour. So in the olden days, we did something called factor labeling, and we canceled out the factors, or the units, if you will, to build the equation. You don't have to memorize any equations. You just have to think logically. Here's what I have. It's a word problem. This is where I want to get to. How do I arrange, okay, the various things I know into the order that will allow me to do that? So the formula for underway time, if you would, time equals distance divided by speed. Okay, time equals distance divided by speed. That's all you need to know. Don't need to know anything else. So time, how much time am I going to spend going from here to here? Well, we know the distance, 5.4 nautical miles. We know the speed, 10 nautical miles per hour. Okay, factor labeling allows us just to cancel out the things that are the same and leaves us with the hours it's going to take for us to get from point 1 to point 3. Turns out time is 0.54 hours. What the heck? Okay, nobody measures time in 0.54 hours. What do we measure time in? Well, if it's not in hours, we're going to measure it in minutes. So we need another calculation to change our 0.54 hours to minutes. We simply multiply by 60 minutes per hour. Okay, if we do that, the hours then cancel. We got 2 of those and only 1 minute left, and we're left with 32 minutes. Excellent. Now we know. We start at 14:52. Okay, it takes 32 minutes at 10 knots to get over here at 0.3. Ah, excellent. Okay, so time of arrival, 14:52 is when we leave. 32 minutes is how long it takes us to get there. Oops, wait a minute. There's only 60 minutes in an hour. So it's only 8 to get to 1500, right? And then you have some left over. We had 32 minutes. We subtracted 8. We had 24. 15:24 is our time of arrival. Voila, we've done it. Time, speed, distance. We've calculated how to get somewhere. You now know how to get from point A to point B anywhere on a chart, I hope. Any comments or questions that you might have, I'll entertain at this point.
Wow, this was a fantastic presentation. I do want to thank you 3 gentlemen up front. So we did get a question. I know we are at our hour, but we'll address one question that came in, which is actually from the beginning of the presentation regarding the Mercator projection. So I know Dane was explaining that a bit about distortion a bit, but someone wrote in, if you could explain the distortion again, as to why Greenland looks so huge and why is Greenland larger than the continent of Africa on the Mercator projection?
Well, it's a projection. So you have to think in terms of, let's say you have a projector, like you used to look at slides using a projector. And if you put a negative or a slide in front of it, and you angle it a little bit, it begins to distort. And that's really what happens when we go back to the very, Shep, maybe you can pop back to that picture because you're still on the screen here.
I can.
Yeah,
At the
just,
beginning, right?
yeah, it's,
Beginning, yeah, let me.
yeah, it's back around slide,
take-
look at slide 12, for example, or
Okay,
whatever. Or just spin back. That'll be good. And you'll see here, a little further.
Further
Yeah, a
up.
little more.
Yeah,
Keep going, yeah. Once you get there, there's a lot of it, so. Okay, right there. Come,
right
Okay.
here,
go to 12.
12,
Yeah,
yep,
okay. So the vision that we're trying to have you visualize is there's a globe, and that's this globe here. And there's a light right in the very middle of it. And so as that light goes in every direction, but as it goes horizontally, there's no distortion at all because the line is actually touching the inside of this cylinder. Think of the cylinder as being a white paper wrapped around the globe. So everything on the equator is going to be exactly the same as it was on the globe. But when you start looking at, let's say 20 degrees north, the light now it has an angle to it. So it's aimed up, and the distortion occurs because of the distance between the edge of the globe and the inside of the cylinder. Well, that's okay, but as you get closer to the pole, now the light is shining up in this direction. It's going almost all the way up to the top of the cylinder. And that makes everything up here much longer. Look at the rectangular box here. This rectangle would be it would be a square if everything was true. But because this projection works the way it does,
like here.
it's perfect along the equator, and it's distorted as you get closer to the poles. Now, that didn't matter much to the old Englishmen and Dutchmen and Belgians who designed this because nobody ever went to the poles. So, the world was near the equator, but it does throw some of those areas way out of proportion. So if you are going to be, let's say, sailing around Greenland or trying to sail the Northwest Passage or something like that, you might want to get the polyconic projection, which shows the poles more true, but the equator is designated or shown. I don't know if I'm making any sense for you, but I'm sure making sense to me.
I think that's a very good explanation. And for anyone that is tuning in or watching the recording, if you're unaware, cartography map making has faced many challenges with taking a round 3D sphere and making an accurate flat representation for our maps and charts. We have a comment here. Okay, so projection is, say, 0 at the equator, and projection towards the South Pole would be larger also. Why isn't Australia larger? That was the question that came in.
Well, as you can see, Australia is actually closer to the equator than we are in the United States. The northern territories and Indonesia, which is the big island just north of it, is pretty much right on the equator. You know, from our situation, if you, you just run that little arrow across the equator, you'll come crashing into Peru in South America right there. Exactly. So that's, you know, and we are more than, or we are a full box, Florida anyway, is a full box north of that. So that's why, that's why Australia seems to be small when in fact it's accurately depicted.
One other interesting thing just to note, this particular projection that you see, the Mercator projection, if you want to sail the shortest route, let's say this is Jacksonville, Florida, from to here somewhere in England, you wouldn't, remember the students of geometry would think, well, the shortest route is a straight line, but not on this projection. In actuality, what you would do, here's, let's say Jacksonville, Florida, is you'd sail way up the coast and you'd go north and then you'd go back down. That's called a great circle route. And that would be the shortest route of sailing miles between Jacksonville, Florida and London, England, not a straight line, which is, we've been taught in geometry, is the, you know, shortest distance between 2 points. That's true on a flat chart or flat piece of paper. It's not true on the projection of the globe at all.
Right, because when you transfer that flat line from a flat chart 2D, if you could pick up that line and place it on a sphere, it's going to curve.
It's going to curve, yes.
Absolutely.
Right.
Absolutely.
Okay, well, that was a great job answering the questions and maybe spark some interest for people out there to maybe study a little bit of how we got to our modern charts and modern maps and investigate some of the challenges there are with getting accurate projections into our hands.
I'd like to make one comment if we can before
Sure.
we quit, okay? And that is that what you see on these charts and what you see on a chart plotter, which is what most people use these days on their boats to navigate, is not real, okay? It's a model of reality. It's an abstraction of reality. And I've seen so many boats come into the marina with their fronts bashed in because they were navigating by chart, or they were navigating by use of their chart plotter, GPS, without looking out the window. And so don't forget to always look out the window, what's in front of you. That's the only thing that's real. What's on the chart is an abstraction or a model of reality. I have to say that in every navigational program I've ever given, because I see it too often where people depend on those things and they think they're real, but they're not.
Well, I'm glad you got the last word in because that's a excellent point. All right. There was a lot of information in this presentation. So even if you joined us live this evening, I would recommend, especially if you are new to reading charts, to come back and watch the recorded version of the presentation, because there are segments that you could pause and perhaps get your own chart out and try and follow along and maybe work through the charting of a course yourself, and it could be very helpful. And if you are taking advantage of using this recording for training, that's another great tip. There's a lot of information and you could really focus in on several segments of this presentation. Again, I can't thank you three enough. This was an excellent presentation with really clear visuals and examples, and easy to follow along. So with that, I will remind all of our Sea Scouts, auxiliaries, and adult Sea Scout leaders that our next U.S. Coast Guard Tech Talk will be on April 26th, where we're going to go further into the topic of charting a course. Thank you for joining us tonight. I hope you learned something, and have a good night, everyone.
Thanks so much.
Good night.
Night.